So in this lecture, we'll cover what are known as standard cell potentials, and we'll also look at what this relative strength of oxidizing and reducing agents. Okay, so this is what a standard hydrogen electrode looks like on the right. So you'd have hydrogen, of course, is a gas, so it's going to be harder to work with because you need to be able to contain the gas and pump gas in and pump gas out. So basically you'd have a source for hydrogen to come in, and then in this particular case, so the reaction we're looking at is 2H plus. So H plus would come into the electrode, so it would pass through the semi-permeable membrane that is selective. It allows H plus to come in, and then in this case you have platinum present, and the platinum is just a catalyst in the reaction, so the reaction occurs on the surface of the platinum. So 2H plus would pick up 2 electrons and make an H2 gas molecule. And so of course you have to have a way for H2 to get out of the flask, otherwise pressure in the container would build up. But the point is that platinum is just a surface for the reaction to occur on. It does not participate in gaining or losing electrons, so it's not part of the oxidation reduction reaction. Okay, so 2H plus 2 electrons, so platinum, we rewrite that on top of the arrow because it's a catalyst to make H2 gas. So that's what a hydrogen electrode would look like, and this is important because it's the standard that everything else is compared against. So you can't measure the potential of one single electrode. All that you can do is measure the difference between 2 electrodes. So everything then is hooked up to a hydrogen electrode and then measure the voltage. And then you have what's known as the cell potential. So in this case, we just have some generic cell set up on the left, and we hook that up to the hydrogen electrode, and then we measure the voltmeter. So if the G generic is zinc in this case, then what you would measure the voltmeter would measure 0.76 volts. So how would we write the cell notation? So for the shorthand notation for the hydrogen cell, so H plus, aqueous, and then a phase transition to make H2 gas, and then it occurs on the platinum surface is the way that you denote that cell. So if we wanted to denote this cell, if it's zinc hooked up to the hydrogen electrode, then you would have zinc solid, goes to zinc 2 plus aqueous solution, and then a salt bridge, and then H plus reacts to make H2 gas, and then it occurs on the surface of the platinum is the way that you would write that cell notation. Okay, so again, then what you would do is you would just change out zinc for something else, change it out for copper, change it out for fluorine gas, change it out for whatever you want to change it to, and then measure the voltmeter, see what the voltage difference is. So hydrogen electrode basically is assigned a potential of 0, so it's the standard, then everything is measured against it, and then what you do is you take these numbers and you put it in a table. In your textbook, it's Appendix I. So if you look in Appendix I for zinc though, so what you'll find is zinc 2 plus 2 electrons to make zinc 0 solid, which would be what you would get if the cell is running this way, from right to left. If zinc 2 plus was picking up electrons and becoming zinc 0. But if this electrode is set up, or this cell is set up such that zinc is the anode and it's given away electrons to make hydrogen gas, then basically zinc is going to zinc 2+, so zinc is losing electrons, so zinc is being oxidized. So that would be an oxidation potential. But appendix I is all reduction potentials. So in the cell that's set up here, if the cell is running from right to left, so if it's running this way, and zinc is given up 2 electrons to H+, which is becoming hydrogen gas, then that would be zinc going to zinc 2+, plus 2 electrons. So that would be an oxidation. Whereas the opposite is a reduction. And everything in the table is wrote as a reduction potential. So if it's oxidation, then the E is 0.76 voltage. If it's a reduction potential, then it's just the opposite sign. So everything in the text, in the appendix, is a reduction potential. So in this case, is zinc 2+ plus 2 electrons to make zinc 0. The potential would be negative 0.76 voltage. Okay, so what we want to do is try to understand these numbers. So the hydrogen electrode is assigned a value of 0, right? It's the standard, then everything is compared to it. So if you coupled this with lithium electrode, you would get negative 3.04 voltage. If you coupled this with a hydrogen electrode or oxygen electrode, you would get a positive 1.23 voltage. And so let's talk about these numbers a little bit to make sure that you understand them. Okay, so lithium and oxygen. Also, and again, note that these are reduction potentials. So reduction is gain, right? Reduction, so oil rig. So reduction is gain of electrons. So lithium is gaining an electron to become lithium 0, or oxygen is gaining electrons and hydrogens to make water. Okay, so, but what do you know about lithium? What do you know about oxygen? So lithium is here. Oxygen is here on the periodic table. So does lithium want to gain or lose electrons? So what charge does lithium want or like to be? So of course it's a group 1 metal. So lithium wants to be +1 charged, right? And what about oxygen? Oxygen wants to be -2 charged, right? So lithium wants to lose 1 electron. Has 3 electrons. It wants to lose 1 electron to be to have the same number of electrons as lithium. So lithium would really rather lose electrons, not gain electrons. So in this case, so lithium gaining 1 electron to become lithium 0, that is not favored. Right, that's not a favorable process for lithium gain an electron. It would rather lose an electron. And that's why E is negative. And it's large and negative. Lithium really does not want to gain an electron. It would really much rather lose an electron. So this would much rather go the opposite direction. Lithium would much rather lose an electron than gain an electron. And if it's oxygen, however, so oxygen, of course, is atomic number 8. It wants to gain 2 electrons. and look like neon. So oxygen does want to gain electrons, and that's why you would see its reduction potential is positive. So positive meaning that reaction is favorable in that direction. If it's negative, it's not favorable in that direction. So oxygen, so if we look in there in the appendix, so what you find is O2 plus 4H plus 4 electrons to go to 2H2O liquid. So E is 1.23, so this is a favorable process. So oxygen wants to gain electrons. So in this reaction, is oxygen serving as an oxidizing or a reducing agent? So O2 gains electrons. So O2 is reduced, which means it is serving as an oxidizing agent. All right, so O2 is a good oxidizing agent. It really wants to gain electrons, which causes the oxidation of something else, and it itself is reduced in the process. So one key to this chapter is really keeping all of that straight in your head, keeping the terminology and the language straight in your head. Lithium, however, wants to lose electrons, so it wants to become oxidized and give electrons to something else. So it wants to cause something else to be reduced, so it's a good reducing agent. So if all of that made sense, so basically as E becomes more negative, it's a better reducing agent. As E becomes more positive, it's a better oxidizing agent. And so if you go into organic chemistry, this will be terms you hear all the time. Different reagents are good oxidizing agents or good reducing agents. If it's good reducing agent, that means it wants to give away electrons to something. If it's a good oxidizing agent, it means it wants to gain electrons from something. So if you take a good oxidizing agent and a good reducing agent and mix them together, you're going to have a pretty powerful reaction on your hands. Okay, so we can use this to answer some basic questions. So if we take this example, so which is a better oxidizing agent? NO3, nitrate, to become NO, or Ag plus to become Ag0. So Ag to become, so Ag plus an electron to become Ag0. So that would be its reduction potential. It's gaining an electron, so it's being reduced. And if you look up in the table, NO3 minus plus 4H plus 3 electrons to become NO gas plus 2H2O liquid. Okay, so let's see. So let's assign oxidation numbers. So what's nitrogen's oxidation number in nitrate? So oxygen's -2, so that's 6 negatives. And so nitrogen must be +5 so that this sums to -1. And then NO on the right, so oxygen's -2, so nitrogen's +2. So basically N +5 +3 electrons goes to N +2. So the nitrogen atom is reduced in the process. But that's beside the point. That's just extra information. You know, you should be able to think through the logic like that, but you don't need that to answer this question. All that you need to do is look at the reduction potentials. So silver +1 electron to become silver 0. Reduction potential, just look that up on the table, was 0.8. And if you look up NO3- to become NO, then this is the entire equation for that process. But its reduction potential is 0.96. So which is more favorable? Well, the one that's more positive. So the reaction that's more favorable is that one, nitrate reduce into NO. So NO3- is a better oxidizing agent than silver plus. So which is a better reducing agent? So what would be reducing agent would be the species that's oxidized. So that would basically be the reverse of these reactions. So if silver goes to silver plus and gives up an electron, then oxidation is lost. So if silver 0 lost an electron, it would be oxidized, and it would be acting as a reducing agent because it would be giving away electrons. Or if NO gave away electrons, 3 electrons, and became NO3-, then it would be oxidized, so it would be serving as a reducing agent. So which is the better reducing agent? Ag0 or NO gas? And the answer would be, well, if NO3- is the better oxidizing agent, then silver 0 is the better reducing agent. Right? They're opposite of each other. And again, you could see that if you just reverse these reactions. So Ag0 goes to Ag plus an electron. So what would E be? It would just be the opposite sign. So it would be negative 0.8. And so NO gas plus 2H2O to become NO3-. Yes, so if it's wrote as a, so these would be oxidation potentials. So if it's wrote as an oxidation potential, then the one that is less negative is the better reducing agent. If wrote as reduction potential, which would be the way it was originally wrote, like these two, then the one that is the one that's less positive or more negative. Then that would be the one that's a better reducing agent. Okay, so hopefully that's not confusing. It's just terminology that you have to keep straight in your head. Okay, let's take another reaction that's similar to that. so if we had this reaction, C2 plus 2I minus to make copper solid plus I2 solid. So which direction? Will this reaction run spontaneously? Okay, so let's write the 2 half reactions. So copper 2 plus 2 electrons goes to copper 0. So that's a reduction potential, right? It's gaining electrons. And then 2I minus. So the oxidation number here is -1, goes to I2. So that's pure iodine, so that would be an oxidation number of 0, and that's its elemental state. So that would have to lose 2 electrons. So that will be, so this is a reduction potential, and this is an oxidation potential. Which means if you look in Appendix I, you'll find the top one copper, but you won't find the bottom one because everything in the table is a reduction potential. So for this one, copper plus 2 electrons will become copper 0. He is 0.34. And so if we take this and write it as a reduction potential instead, so if we just reverse this, so this would be what you find in the table. So 0.54. Okay, so which of those is more favorable? Well, this one's more positive, so this will be the reduction potential that is more favorable. So basically what this means is that I2 would rather gain electrons, just like the reaction shows. I2 gains electrons to become I2I minus, would rather gain electrons than copper 2. Okay, so if we go back to the reaction, so copper 2 plus 2 electrons to become copper 0. So that would be if the reaction proceeds right to left, and if the reaction proceeds left to right, then I2 gains 2 electrons to become I minus. So which of those two processes is more favorable? Well, this right here. Right. I2 plus 2 electrons to become 2I minus is more favorable than copper 2 plus 2 electrons to become copper 0. So this reaction would rather go in reverse direction, not the forward reaction. So it's spontaneous in the reverse direction. So if you hook up those two cells, then the way that they're going to work is I2 is going to gain electrons from copper to become copper 2 and 2I minuses. Okay.